Okay, in the previous class, we talked about shaft design. We talked about stress concentration factor, the slope and deflection requirements for mounting the components on shafts and designing for that, and finding out, the diameter for the shaft considering the stresses and all those components. ठीक है जी. Let's talk about critical speed for a shaft. So, what is critical speed for a shaft? Basically, if we look at a shaft, it rotates, and a shaft with mass has a critical speed at which its deflection become unstable. If you look at a shaft, it will be deflected somehow. Like for example, if this is a shaft, we do agree that there is deflection in the shaft. It's never going to be very, very straight, right? And since there is deflection, when it rotates, what's going to happen when it rotates? The shaft is going to vibrate. ठीक है जी? So components attached to the shaft have even a lower critical speed than the shaft. And designer should ensure that the lowest critical speed is at least twice the operating speed. So, what is the critical speed? Critical speed is that speed at which uh, the resonance will occur, at which the natural frequency and the excitation frequency become the same. ठीक है. So that is going to be our the critical speed. So what we will try to do is that when we design shafts, we will ensure that the lower critical speed, which is the first natural frequency, is at least twice the operating speed, so that it does not reach there. Um, for a simply supported shaft of uniform diameter, the first critical speed, we already know this, K, from your physics, in your metric, and कि आपका जो फर्स्ट क्रिटिकल स्पीड है ओमेगा वन, दैट इज इक्वल टू पाई बाय एल स्क्वेयर ई आई ओवर एम अंडर द रूट. ठीक है जी. Or it is pi over L square, instead of writing m, that is a gamma over g. ठीक है जी. EI, so it will be pi over L square GEI over gamma times A. ठीक है जी. For an ensemble of attachments, there is Rayleigh's method for lumped mass, and with that formula, your omega 1 is G times Wi yi over sum of Wi yi square, um, where we will describe these. For example, the critical speed for a shaft, equation 7-23, which is this one, the Rayleigh's method for lumped mass, can be applied to a shaft itself by partitioning the shaft into segments. For example, let's say that this is a shaft. So what do we do to the shaft? That these are the supports for the shaft. Let's say this is y and this is x-axis. So what we will do is we will separate this shaft into 1, 2, 3, 4, 5, and 6. For example, these partitions, and we will assume that the mass of these partitions is over here for the first one, over here for the second one, third one, fourth one, fifth one, and sixth one. So we will say that this weight Wi is acting over here, which is W1, W2, W3, W4, 5, and 6. So For this, what we do is that there is an influence coefficient that we use, and that is that an influence coefficient is the transverse deflection at location I. This is a small I. Okay? At location I due to load, unit load at location J. What we mean here is, like, let's say, for example, we have a shaft over here. Okay? Now, let's say that there is load over here, and let's call this load P1. And there is another load over here, which is P2. Now, if we look at the deflection of this shaft, let's assume that the deflection somehow is like this. Okay? Now, what if this P2 was not there? Okay? Let's say if this load was not here, right? So then what would have been the deflection? Would it have been the same or different? It might have been like this. So if we include this load P2, then the deflection at both, you know, everywhere changes. Therefore, this load P1 and this load P2 has the deflection effect. The effect of this deflection is throughout the span of the shaft. So let's say if this is location 1 and this is location 2. So there is deflection over here due to load P1, and there is also deflection due to load P2 over here at this location 1. Similarly, over here, there is deflection due to load P1 and due to load P2. So at both these locations 1 and 2, there is deflection due to the both the loads P1 and P2. And that is why what we call the influence coefficient. Okay, what is influence coefficient? It is the transverse deflection at location I due to unit load at location J. So, for example, if this is my I and this is my J, ठीक है जी, locations, and we have I load and J load. So the deflection due to load J at I will be the influence coefficient if we consider J as the unit load. ठीक है जी. Now, from table A9-6 for simply supported beam with single unit load, आपका जो delta ij, which is known as the influence coefficient, that is equal to bjxi 6eil into l square minus bj square minus xi square, or and that is for xi is when the length, when the xi is less than or equal to ai, then you will use this formula to calculate your influence coefficient. Or if xi is greater than ai, then you will use this formula to calculate your ai, your delta ij. ठीक है जी. Now, and what is bj, xi, and ai? The map is given to you. Okay, this is ai, bj, and xi for a beam in order to calculate that, where your L is the span between the supports. ठीक है जी. So you can use that formula to find the stress in the influence coefficient, and now we will use this influence coefficient taking for example, a simply supported beam shaft with 3 loads. Okay? Let's say that we have 3 loads. The deflection corresponding to the location of each load is, let's say, if for example we have three loads, okay? So we'll have F1, F2, and F3 load, right? So, or deflection over here, let's say that is y1, over here the deflection is y2, and over here the deflection is y3. So what will we have with y1 will be equal to the deflection due to load F1 times delta 11, which is the influence coefficient over here. ठीक है जी. Similarly, F2 times delta 12 plus F3 times delta 13. So that is the deflection over here due to load F2 and the deflection over here due to load F3. So that is why we are adding all these components. ठीक है जी. Similarly, y2 will be equal to f1 delta 21, f2 delta 22, f3 delta 23, and y3 will be equal to f1 delta 31, f2 f2 uh, delta 31, and f2 delta 32, and f3 delta 33. If the forces are due to only the centrifugal force because it's rotating due to the shaft mass, then we can write the force which will be equal to m omega square, m1 omega square के बराबर हो जाएगा, ठीक है जी, times y1. So which is the deflection, so we will go ahead and write that. So m1 omega 1 square y1 delta 11, m2 omega 2 square y2 delta 12, and so on. So we will write those three equations over here in this form. Rearranging these equations, what we will have is k m1 delta 11 minus 1 over omega square y1 plus m2 delta 12 y2 and m3 delta 13 y3. um, and similarly for the other two equation, equal, we will equate these to 0, and that's what we will have. Okay? Now for a non-trivial solution, we will take the determinant of these we will write the coefficients of y1, y2, and y3. So that makes a matrix. For example, the first coefficient is this one, the second one is this one. So let's take these, and the determinant, uh, the determinant, if we want to solve these equations, so for non-trivial solution, the set of simultaneous equations will exist when its determinant is equal to 0, then we will say that the solution exists. So expanding this determinant, what we will get is, we can write, I'll move to the solution that we can write in terms of its three roots, which will be 1 over omega square minus 1 over omega 1 square, 1 over omega square minus 1 over omega 2 square, 1 over omega square minus 1 over omega 3 square is equal to 0. ठीक है जी. Or what we will have is, comparing equation 7-23 and 7-28, 1 over omega 1 square plus 1 over omega 2 square plus 1 over omega 3 square is equal to m1 delta 1, m2 delta 22, m3 delta 33. Now, defining this omega I as the critical speed if mi is acting alone. If only one one of the loads is acting, so then this equation becomes 1 over omega I square is equal to mi delta II. Looking at this over here, if there is one load, that will be 1 over omega II, ठीक है जी, 1 is equal to just mi delta I. So thus 7-9 can be written as 1 over omega 1 square plus 1 over omega 2 square plus 1 over omega 3 square is equal to 1 over omega 1 1 square, 1 over omega 2 2 square, over plus 1 over omega 3 3 square. Now, but what is critical speed? What is critical? What is omega 1? That is the first critical speed. Omega 2 is the second critical speed. Omega 3 is the third critical speed. So the first critical speed basically arrives earlier, or that is the first one, that is the the lowest speed. Therefore देखें ओमेगा 1 जो है, what is omega 1? ओमेगा 1 क्या होगा? अगर इसका रिसिप्रोकल में ले लूं, राइट, सो दिस इज द फर्स्ट स्पीड विच इज लोअर. तो एक लोअर नंबर का मैं अगर रिसिप्रोकल लेता हूं 1 ओमेगा 1 स्क्वायर, दैट विल बी वेरी वेरी लेस देन 1 ओवर ओमेगा 2 स्क्वायर, and that will be very very less than 1 over omega 3 square, because the reciprocal of a smaller number is going to be a bigger number. ठीक है जी. तो therefore अगर हम उसी equation 7-3, if we look at this 7-30, we can ignore some of the terms. For example, देखें, we are taking 1 over a smaller term square, 1 over the square of a term. ठीक है जी. So the square of a bigger term and the reciprocal of that is very very small. Therefore we can ignore these terms, these two terms. ठीक है जी. So if we ignore these two terms, 1 over omega 1 square is equal to 1 over omega, almost equal to 1 over omega 1 1 square plus 1 over omega 2 2 square plus 1 over omega 3 3 square. And therefore expanding this idea to n body shaft, we obtain an equation which is known as Dunkerly's equation. And Dunkerly's equation says, it's just this equation that says that 1 over omega 1 square is the sum of 1 over omega I square. If you have a shaft that has, you know, n number of these bodies, then you can say 1 over omega 1 1 square, 1 over omega 2 2 square, or 3 3 square, and so on up to 1 over omega n square. Okay? So this is your Dunkerly's equation. Now, critical speed for a shaft with the since Dunkerly's equation um, has loads appearing in the equation. Okay, if you look over here, it has loads that are appearing in the equation. It follows that if loads could be placed at some convenient location, transformed into equivalent load, then um, the critical speed of an array of loads could be found by summing the equivalent. So what is the convenient location for placing the load? We already said the convenient location for placing the load will be the center of these bodies. ठीक है जी. The for every section, what we will do is you can place this at the center. ठीक है जी. Concentrate the load at the center. Therefore omega 1 1 square is equal to 1 over m1 delta 1 1 is equal to g over w1 delta 1 1. We wrote m as w over g over w1c. And what does this c stand for? This c stands for the center. ठीक है जी. So the delta at the centers will be delta cc. So we can write that W1C is equal to W1 delta 11 over delta CC. ठीक है जी. So you can incorporate that in that equation. ठीक है जी. Let's look at this problem, and I hope that you will understand this by doing this problem. Let's see. It says that Consider a simply supported steel shaft as depicted in the figure, which with 1 inch diameter and 31 inches span between the bearings, carrying two gears weighing 35 and 55 pound force. So find the influence coefficient. So you can find the influence coefficients, right? Delta 1 1 and delta 1 2 will be your influence coefficients. Okay? And we have formulas for that, as we already discussed. Okay? So find the sum of wy and the sum of wy squares, which we will use in the equations, and find the critical speeds using Rayleigh's equation. So these are used in the Rayleigh's equations. That's why he wants us to calculate. From the influence coefficient, find omega 1 1 and omega 2 2. Using Dunkerly's equation, 7-32, estimate the first critical speed. Use superposition to estimate the first critical speed and estimate the shaft's intrinsic critical speed. Suggest a modified Dunkerly's equation to include the effect of the shaft mass on the critical speed of the attachment. ठीक है जी. So this is what we have this shaft. ठीक है जी. This is the span of the shaft over here, which is 31 inches, and we have these two loads, two gears basically are mounted. One is 35 pound force, the load over here, and the other one is 55 pound force, and the distances are given as 7 inches, 13 inches, and 11 inches. Okay? So let's see what we can do. First of all, go and find out your I, which is pi by 64 d4. Okay? For the shaft, and if you put in the values of d, which is 1 inch, so that will be pi by 64, and that comes out to be 0.04909 inch cube, inch 4. Go ahead and find your 6EIL, because we are going to use this equation, which was the for delta II, and let me use this one. Okay? So that's why we want to find out this 6EI over L. Okay? So we can find our delta 1 1 and delta 2 2 from that. ठीक है जी. तो हमने ये मालूम कर दिया, which is 0.2739. So looking at that equation 7-4, the set of equations, you can go ahead and find your delta 1 1 and delta 2 2 by just plugging in the values over here. ठीक है जी. So you have delta 1 1 and delta 2 2 now. Also, you will have delta 1 2 and delta 2 1. ठीक है जी. And you will have these three: delta 1 1, delta 1 2, and delta 2 1, which we assume that it is equal to delta 1 2. ठीक है जी. तो ये चार आपके पास चार आपके पास इन्फ्लुएंस कोएफिशिएंट्स होंगे, बिकॉज वी नो कि आपका y1 जो है, which is the deflection due to load 1 and load 2 at this location. ठीक है जी. This is your y1. So we know कि y1 is equal to w1 delta 1 1 plus w2 delta 1 2. Similarly, आपका जो delta y2 है, you will have two equations over here. In the previous case that we just looked at, for the analytical solution, we considered three loads. But in this problem, we have two loads, so we'll have w1 delta 2 1 plus w2 delta 2 2. ठीक है जी. तो ये हमारे दो equations we'll have, and let's put in the values of the delta 11 and delta 12 and W1 and W2. We know that one is 35 and the other one is 55. So 35 and 55, and put the values of your delta 11, delta 12, delta 21 and delta 22. So you will calculate your deflections from here. Go ahead and find your W1 yi. ठीक है जी. Similarly, the sum of wi square, we know that omega is equal to what? That omega is equal to, if I go up, let's see, this was our omega. It is g times sum of wiyi and over sum of wiyi square. So using this equation, you will find out your ओमेगा. ठीक है जी. तो ये हमारे पास ओमेगा आ गया, which is 124.8 radians per second or 1192 revolutions per minute. ठीक है जी. Now go ahead and find your 1 over omega 11 square, which is equal to W over G times delta 11. So omega 1 is equal to G over W1 delta 11 under the root. And similarly, W22, the omega 22 is equal to G over W2 delta 22. Putting the values, you will get the revolutions per minute or radians per second for omega 11 and omega 22. Now, you can go ahead and find out your 1 over omega 1 square, which will be the sum of 1 over omega I square. Now, putting the values from the above equations, यहाँ पे जो values आपने find out किए W11 and W22, omega 11 and omega 22, just put those values 1 over omega 11 plus 1 over omega 22. You will find your omega 1 from here. ठीक है जी. Now, which is less than part B as expected. ठीक है जी. तो there is a difference between the both the आपने दो तरीकों से मालूम किया है, and this is a little bit less than that. ठीक है जी. From equation 7 dash to 4, you go ahead and find your delta CC, जो अभी हम कह रहे थे कि you place that at the best location, which is the center. So go ahead and do that. Your delta CC and W1C, W2C, जिस तरह पिछले part में we went ahead and find that. So you can find your omega from that, which is 120.4 radians and 1150 revolutions per minute. ठीक है जी. और अगर आप इसको देखें, in part E and in part D, they are almost the same. ठीक है जी. D में and it is 120 point, omega 1 is 120.3 radians per second, and we also got the same 120.4 radians per second. ठीक है जी. अच्छा जी. He again says that superimpose both the loads on each other. तो देखें, सुपर इम्पोजिशन के लिए हम क्या करेंगे? We will take the loads at the very center, both the loads at the very center. So one was 17.1 pound force and 46.1 pound force. ठीक है जी. दोनों को लेके W1C and W2C, and we will superimpose that and put it at the center. And from that, now we can go ahead and find our 1 over omega 1 square and omega square. ठीक है जी. And using the same equation, we will do that. और फिर हम उसी डंकरलीज इक्वेशन को थोड़ा सा मॉडिफाई कर रहे हैं. We are just adding, one part in this. So go ahead and look at that कि हम इसको कैसे you know since the equation does not fit into the summation, it is usually written up front. तो generally मतलब हमने इसके साथ ये summation में we added this part up. ठीक है जी. um, so that was about the critical speed. Okay, you can find out the critical speed. ठीक है जी. And now what will you do once you find out the critical speed? क्या करेंगे? What will you do once you find out the critical speed? You will try to keep the operating speed far away from this. और हमने क्या कहा था कि at least twice, so that you do not have the so that you do not have an issue with resonance and failure of the shaft. ठीक है जी. Hello.
Yes, sir.
You guys.
जी सर, जी सर.
Now let's say when we put components on shaft, we use different um, torque transfer components. For example, set screws, keys, pins, and so on. ये हम इस्तेमाल करते हैं. Now set screws resist axial and rotational moment. देखिए set screw, let's say if this is a pulley, you put this on a shaft with a hub. ठीक है जी. यहाँ पे hub होगा and you put in a set screw over here. ठीक है जी. So all these set screws, keys and pins, they are standard. The tip of the set screw may also provide a slight penetration into the shaft.